Okay, welcome back. In this little bit of chemistry here, I want to show you the condensation of a carboxylic acid with an amine, in this case an unprotonated amine, to form an amide. This amino group here, unprotonated, has this non-bonded electron pair, this lone pair, and that of course is electron rich. And that electron-rich nitrogen can nucleophilically attack this carbonyl carbon. Because of its electron deficiency, we are going to try to form a bond here between that nitrogen and that carbon. And carbon's already got 4 bonds, so as with esterification and so forth, this carbonyl is going to open up to an intermediate that has a fully charged oxygen atom in it. So this looks just like it did with esters, thioesters, this intermediate. We've got the structure like this, and then that new bond with the nitrogen of the amine here. And now as you see, that nitrogen has 1, 2, 3, 4 bonds, so that nitrogen is actually positively charged. Okay, and just like with esterification, we can eliminate that charge by moving a proton over to that OH group. That gives us a second intermediate. Looks like this. Okay, we're not changing anything with the oxygen atom yet. But what we have done is we've created a protonated OH group. Okay, there's 1 free electron pair there, and that actually makes that oxygen positively charged. And now we've neutralized the nitrogen atom. It's got its lone pair like that. So this part of the molecule is neutral, and this part of the molecule is positively charged. This part of the transition is negatively charged. Just like in esterification or any of these condensation reactions, we can now remove that water, move these electrons into the double bonded pair here, and that's going to generate our amide. And so with this, we have regenerated double bonded oxygen, and we've got now this structure here, which is our amide. Don't forget the hydrogen atom there. Could be a little neater. Okay, and that's our amide. And of course, we eliminated water here, so to balance everything out, we'll put the water in there. And that is the condensation of an amine with a carboxylic acid to give us this amide. Of course, these reactions are all reversible. The oxygen here can attack that carbonyl and open it up into this intermediate. And of course, we can transfer that proton back onto the N here, generating this intermediate, and then we can eliminate that amine, regenerating our free amine and our carboxylic acid. So all of this is reversible. Amides are fairly stable. They're a little bit harder to hydrolyze than, let's say, thioesters or maybe even normal esters, but it is reversible in that, and they can be hydrolyzed. One thing you want to pay attention to here in this structure here, this is the amide bond. This particular bond here between that carbon and that nitrogen has some double bond character. I'm going to show you some tautomeric forms of this. Okay, these are equivalent forms. What I can do is I can move this non-bonded electron pair, form a double bond there, and move that electron pair out, and I could generate this equivalent form. Okay, what I'm trying to do here is to show you, is the double bond nature of the bond between that carbon and the nitrogen in the amide. So you can see this bond here is equivalent with that double bond. And so some of the time, you can think of it, some of the time the molecule exists in this, and some of the time the molecule exists in like that. Sorry, I left the hydrogen out here. Okay, and we also have a charge on this, right? Because we've got 1, 2, 3, 4 bonded nitrogen. Okay, and so this whole tautomeric form is equivalent with that. We can actually neutralize those charges by moving that proton from the nitrogen over to the oxygen. And that gives us another form here where we have our carbon, oxygen, hydrogen. This one's all neutral, happy. This one here as well. So these three forms are equivalent tautomeric forms, and what you can see from this is that that bond between that carbon and that nitrogen in the amide structure has double bond character through these equivalent forms. And that makes this whole thing a flat and rigid planar structure. This bond here does not easily rotate because of that double bond nature. Okay, and so you can think of that amide bond as sort of a flat, solid unit. We have rotatable single bonds here between that carbon and that R group, and we have a rotatable single bond here between that nitrogen and that R prime group. But this bond here between the carbonyl carbon and the nitrogen of the amide, because of that double bond character, is not rotatable and acts like a unit. Okay, that's the condensation of an acid and an amine and the formation of amide. Thanks for listening.